Hey guys, like I told you before, you're probably watching this while I'm in Paris. So this is chapter 2 in ISE 327. This one's on systems approach and system engineering. So hopefully you guys can watch this video. It's going to be posted on YouTube. That's what our plan is. And so you guys can watch this while I'm gone. Remember, the slides are on Angel under the class lectures. So remember to download those, and you can use those because I don't know how well you can see the screen, but it's kind of the best we've got right now. So in chapter 2, the objectives, what we're supposed to do is figure out what a system is and what is system engineering. A lot of people have different definitions of system engineering, so we'll give you the one that's in the book that you work with and the one that kind of I like, and then we'll go from there. So we'll use that one. We need to identify the key system component concepts and principles. We're going to talk about the input process output model and how you can use it to solve problems. We're going to do some stuff on systems approach, how the system approach is different from the classic scientific method approach. And then we're going to talk about the phases of the DoD system life cycle, and even we'll go into the stages because there's an appendix in your book, and so I highlight some of that as well in the book. So, definition of a system. A system is an organized or complex whole, a group of parts interacting in a coordinated way, right? And that's a big part to this. They must be performing some global function together, and that defines a system, right? So the parts of the system affect the system and are affected by it, so everything is working together. These are the interfaces. So the parts of the system could be the subsystems, the components, the elements, whatever. They're all working together to accomplish some sort of job or function, right? And so that's what a system is. The group of the parts does something, and that's the big part to it. And the group is of a particular interest, right? So whatever it's doing, it's of particular interest to someone, and so that defines a system, okay? So there's system concepts and principles as well. So there's the nature versus human-made system, right? And natural systems, God, not nature-made. Natural systems versus human-made systems. Natural systems are animal organisms and planetary systems, right? Human-made systems are communication systems and human organizations. Basically, we made them, right? That's a human-made organization, human-made system. A natural system occurs in nature naturally. This kind of makes sense, right? So projects exist for the purpose of creating or enhancing human-made systems or altering natural systems. We do not create natural systems, you know? That doesn't happen for us. Everything that exists in the environment was created. We didn't do it, right? So all we can do is create or enhance a human-made system or alter a natural system. All of those are projects that we can do. The goals and objectives, basically, of a human-made systems are designed to do something. They have goals and objectives that are conceived by people, right? So this makes sense. In designing a human-made system, the place to start is by defining the goal of the system and a hierarchy of objectives that relate to the aspects of the system. This is the beginning of systems engineering, if you think about it. Because now we know that we want this goal of the system, right? So this could be what the customer's need or want is. And then we create this hierarchy of objectives to determine the aspects of the system that we need to do. So you can get, the primary objective, the secondary objective, all of that can come out, and then you can really understand what the system should do. There's also elements and subsystems of a system, right? And so systems can be broken down into smaller parts. These parts in combination form the assemblage of parts. The smallest part of a system is an element, and the parts of the system might themselves also be systems, but they're called subsystems, okay? Whatever you define a system to be, it's really in the eye of the beholder, right? Someone could have a subsystem. A spacecraft, for example, has several subsystems. So we would call the spacecraft the system, and then propulsion, guidance, navigation, control, thermal are separate subsystems. Now to the thermal guy, the thermal subsystem is his system, okay? So it's really what perspective you have in all of this, where you draw your boundary line as to what your system is. So that's very important to remember. So when you define a system, you need to clearly define it and clearly define the boundary of it, so you make sure you always say the right thing, right? Because there's no rhyme or reason to this. It's just whatever logically fits in the project you're working on, okay? So you can look at even as a company as a system, right? So the whole system is all of it, right? So you have management, you have functional subsystems, personnel, marketing, production. Then production could even be broken down from the subsystem level into more definite parts, right? And it can continue to go down to where you get elements, okay? Same thing is true for a hardware thing, right? So you could take a propulsion or a spacecraft, right? And I'm a propulsion guy, so I'll use it as an example. Spacecraft is the system, propulsion is the subsystem, and then you can go below that into the tanks, the rocket engine, the lines, everything. And so you continue to break it down into the pieces that you need it to. You have to define what is best for your system, right? And you can create a breakdown structure to know which level what things are in, and that can work for you really well. But that's kind of what you have to do as a system engineer or the project manager. Usually when you create a WBS, a work breakdown structure, which is a part of managing a project, you usually pull it to the level that you want to manage it to. And so likewise with a system, you would take it to the level that you want to understand the most about, okay? And that's the most important. Do you really care that there are 75 washers on this thing? Or do you care that there's 2 tanks? You know, you can see the level of difference in the detail that you got there. Because more detail adds time and money, and you might not have that as a project manager. So you have to worry about that as well. So there's attributes of a system, right? So systems, subsystems, and elements each have distinguishing characteristics that we call attributes, right? These attributes describe or express the condition of a system, the subsystem, or element in a qualitative or quantitative terms, okay? So all systems have attributes. They have characteristics that we can help define them with, okay? In human-made systems, many of the attributes are designed into the system so that the system performs as required, right? So that's the thing. The attributes end up helping you verify your requirements. You're checking the boxes. Compliance is what you're after. So those attributes can help you do that. There's a system structure where elements and subsystems are linked together by relationships, right? Like I said before, see, I kind of started at the top. I'm a top-down guy. So you have the system, the spacecraft, and then you have all these subsystems, and how they all link together forms this system structure to create the system, right? It's not a physical structure. It's a way of looking at it on a piece of paper to make sure you've got everything there more than anything. So most systems, including projects, can be conceptualized as hierarchical and network systems, right? That's all they are, is put them on the top, put the things, and then everything flows down from there, right? System, subsystem, elements. And there you can understand every piece that you need to make sure and manage, because that's the point, right? You want to make sure and manage all of this. There's also the environment and the boundary, which I've already alluded to, right? So the environment refers to anything that influences the behavior or the outcome of the system, yet lies beyond the decision maker or stakeholder's ability to control. That's the scary area, right? So the environment, literally for us, like in spacecraft design and what most of you will do next year in IPT, that's the environment that's there, right? We're going to Europa, which is at Jupiter. We cannot control that environment. We cannot control anything it does, right? We have to deal with it. So we got to design to meet it and to handle it as long as we need it to. So that's what we've got to do. The system is separated from its environment by a boundary. So that's truly what defines the system, is the boundary around the environment, right? The boundary might be somewhat obscure and it might be difficult to distinguish the system from its environment, but you need to do that. You need to be able to pull it out, be able to say, this is the system. I can control everything with this system, right? Anything I can't control must go into the environment, and I just have to design to survive it or handle it, right? So all that is a part of the system engineer's job. It's truly define the boundary. What can we as humans control, and what do we have to live with, right? So that's the job of the system engineer. The input process output model, it's kind of a duh if you think about it, but it's kind of how we define a system and what all it does. So human-made systems achieve objectives by converting inputs into outputs through a defined process, right? That's all we do, is we send something in to a system, it outputs something out of it, right? On the other side, if we look at the model, And in between, some process happened. That's a black box right now to us. It's just a process, right? So the outputs are the end result of the system and the purpose for which the system exists, right? We put something into it. The output is why we created the system in the first place, to get something done, to get the job done, right? We had to give it some sort of input, and then it did it on the output. It's kind of like a computer program, if you want to look at it that way. The computer program could be the system, right? We code in inputs, it runs some algorithm or something we created, and the output, the result, is what we're after, right? So the inputs are the raw materials, the resources, are prior steps necessary for the system to operate, produce outputs, and meet objectives, right? So all that's what we're after. Feedback basically is the input that originates from the system itself, so you can have this feedback loop to make things better, right? And process is the means by which the system transforms into inputs and outputs. So one goal of the system design is to create a process that produces the desired outputs and meets the system's objectives effectively and minimizes consumption of inputs and production of wasteful outputs. So you want a very efficient system that the least amount of input gives us exactly the output we want, right? And so that's basically what we're trying to do, is get us all of that effectively and efficiently, okay? So you can see the model. It's kind of simple. I mean, you've probably seen this before, but it's a system model. So you have the inputs. They are fed into the process. And right now, like I said, the process to a system engineer is a black box. That's the designer's job, really. We don't care. At the system level, we don't care. Just somehow it happens, and here's the output, right? And then you need to make sure match the output to the objective, and then give feedback to maybe make this more efficient on down the line, right? So this can be a loop for a while until everything gets correct. So it's kind of a standard, simple thing if you look at it from that perspective. In the systems approach, basically we acknowledge that the behavior of any one element affects the behavior of others, and that no single element can perform effectively without the help from others, right? So again, we're looking at this big approach like we talked about in chapter 1. The system approach means everything we do, everything inside this system has to work with other things to make the overall thing work, right? So that's the systems approach to it. Because traditionally in propulsion and spacecraft design, in anything, the propulsion guy is usually just thinking about propulsion and nothing else. That's not the system approach. The system approach is, when I do things in propulsion, I'm affecting other people, and I need to make sure that is at least communicated to them, because I will want anybody who does it. In the subsystem areas, especially in design and engineering, we each want to optimize our own. And really what happens is we need to optimize the system at the top. And so each of these things have to give and take a little, right? So no subsystem is actually optimized for itself. The system as a whole is optimized instead. And that's the system approach, is to make sure all that happens. Because if you don't, it can be disastrous for any design, right? So the system approach recognizes interdependencies and the cause-effect relationship among elements, right? I can change my thing, and it will affect someone else. So you've got to remember that. We have classic examples in senior design of people forgetting that, and they go off and do their own thing on their own subsystem and make it better, but they forget it affects everybody else. And then the design collapses. It's what we call, it doesn't close. The entire loop doesn't close, and the system as a whole work anymore. And so you've got to make sure that happens. As a system engineer, that's really one of your jobs, is to make sure all of that happens. And as the project manager too, right? You've got to make sure all of that comes together so the communication paths are open and flowing, you know? The system approach retains attention on the overall system and the ultimate goal. It allows focus on the parts, but only in regard to their contribution to the whole system. So that's all we're looking at, is this big thing, the big system and how it goes together, right? It avoids actions that focus exclusively on parts of the system, since such actions are suboptimal for the total system. So we talked about that already. All that happens. The methodology is for solving problems and managing systems, right? And so the methodology commonly employs models, right? So the systems approach, you're going to have all these different models. These could be physical models. These can be computer models. Anything you can think of as a model can be used to make this methodology happen, right? Because you can have models interact with each other and figure out things. You can do all of that. So all of that is a part of the systems approach. So it's basically, you just solve the problems and manage the systems. That's all you have to do, is keep solving the problems. You know, a problem's going to creep up in a system and you have to look at it and solve it, but at the system level. So make sure everybody is aware of it, because things are going to happen, right? And so that's what you have to do, but you have to keep the system in mind the whole time. So the life cycle, right? A system always has a life cycle. Any system we design. It must go from conception, or, you know, preliminary design, or not even preliminary design, just the beginning of the design, right? Conception all the way through operations, maintainability, sustainability, and disposal have to be thought of in these systems, okay? So the system life cycle is a pattern of change or evolution that similar kinds of systems follow. The basic life cycle of all organisms is the pattern of conception, birth, growth, maturity, you grow old, and then there's death, right? And so all systems do this. All natural systems, all human-made systems do this. Conception happens, right? We create the thing. We literally develop it, get it ready. It continues to grow and mature and gets old, and then finally it's obsolete and it's gone, right? So the aerospace systems are kind of that way as well. And this life cycle for an aerospace system could be 100 years. The B-52 bomber is exactly that. From the time we started the idea until probably when they're actually mothballed, it's going to be about 100 years. So these things can last for a very long time, in the aerospace world especially. So the basic life cycle of a human design system is a series of logical, structured steps called the systems development cycle, okay? Or we call it the system engineering process. I mean, there's lots of other terms for it. The cycle has phases of conception, definition, design, development, fabrication, testing, installation or launch, production, operation and maintenance, and enhancement, replacement or termination, right? It depends on who you work for and what you're doing as to how many of these phases are combined together. Some organizations put a lot of them together, some of them don't. So, but they're all kind of that way. They're about the same thing. The prescribed stages or phases for large-scale development projects is called system engineering, right? So once it becomes something real, we usually call it system engineering. The system development cycle is usually kind of not used anymore. Okay. So this is DoD's system engineering process, or system engineering way. So they have concept refinement as the first stage, phase. The second phase is technology development. Third phase is system development and demonstration. Their fourth phase is production and deployment, and they have operations and support, okay? And so they even don't really look at disposal. NASA has pre-phase A up to phase EF, which is operations and disposal. So you can see this is kind of pre-system engineering acquisition, this is system acquisition, this is sustainment. And you have milestones along the way where you got to make sure you meet certain objectives, certain requirements of a system have to be done by that point. And so you've got all these reviews, and so it can be a nightmare. It depends. Truly, the system engineering process can be very flexible, but you have to understand the system enough to know how to change it. Because the system engineering process, it isn't like a cookbook that you can just flip open and go, oh, okay, do this and this and this and this, and that makes a system. No, you got to understand your problem really well, and once you do, you can make the system engineering process work for you. We've had a pendulum swing in the government, especially in the late 90s. System engineering kind of went away. We went down that path because everybody thought it was just the fluff and nobody needed it. If you look at the early 2000s, late 90s, early 2000s, when we did that, projects started tanking really fast. There was no way to know if requirements were being met, if anything was happening. And so the pendulum swung the other way, and we got to a point where system engineering, everything had to go through the system engineering process, and you had to go through every step. And so it became so crazy that before you could even purchase carpet in a facility in a government facility, you had to go through the system engineering process. You don't need to do that to purchase carpet. When it's needed, when it's a really big decision you need to make, then use the system engineering process to help you make it and to figure out what to do. But don't do it for everything because it's just too much work. So I think the pendulum is starting to swing back to the normal state, which is just use common sense, right? You can understand when it's time to use the system engineering process and when not. And usually the your higher ups, upper management usually know when this is appropriate and when it's not. So system engineering, what is that, right? So it's the science of designing complex systems in their totality to ensure that the components and subsystems making up the system are designed, fitted together, checked, and operated in the most efficient way. Okay? It is also the conception, design, and development of complex systems where the components themselves must be designed, developed, and integrated together. That's another definition. And another one is a way to bring a whole system into being and to account for its whole life cycle, including operation and phase out during its early conception and design. Right? So all of those are definitions. One thing you can see always is there's usually a complex system or a whole system. It's being developed from beginning to end, right? All of that is a part of system engineering. So, and the problem is, classically in system engineering, we are really great at the end of the phases, at the end of the process. System engineering is really seen as something valuable. There's not as much done in the upfront stuff, the conception and the birth part of it. That's where system engineering lacks most of all. And so that's actually what I like to do the most, is the upfront stuff. So system engineering has to take on that role more and more, because it's supposed to. So you can see this is the classic system engineering V, is what it's called. This is the V model in system engineering. So we have this stakeholder objectives, right? And that starts us out. And then we go into system design, subsystem design, component design, implementation, and it always goes up to integration and validation. And so we got to make sure there's this feedback loop in there. Then we got fabrication, right? And we test it and make sure everything's good to go. So that's the classic V going up and down of system engineering. That's the V model that a lot of people talk about. So that's one of the models of system engineering. There are a lot. There are different stages of system engineering, right? And this is actually the appendix in the book, at least in the 3rd edition of the book. I hope the 4th edition is the same way. SE has a much wider role than ordinary engineering, right? Mechanical engineering, aerospace engineering, all those have very focused areas there to look at, right? Aerospace does aerospace stuff. Mechanical does the mechanical stuff. System engineering does it all, you know? It's all over. It's got to be from in aerospace engineering, it's in mechanical engineering, it's in electrical, it's in optical, it's in civil, it's in biomedical, you know, it's in all of them. And so we've got to realize that when we're doing it. Basically, it's the logical process employed in the evolution of a system from the point when a need is first identified through the system's planning, design, construction, and ultimate deployment and operation by the user, and disposal. That should be on there as well, right? We've got to worry about that. There are kind of 3 lumped together overall phases of system engineering. You can put them all kinds of buckets and call them different things, but there's 3 kind of overall areas. There's development. So we created the system, right? We started out with a user's need, and we went all the way, or customer's need. We went all the way to, ta-da, here it is, right? We've now done it. We've designed it. It's ready to go. We then produce it. We can mass produce it. We might just create one of them, whatever. Then we produce it, right? And then we use it, right? So utilization is we use it, we get rid of it, we dispose it, okay? So those are the 3 overall phases that we go through. In the first part is needs identification and conceptual design. This is called stage 1 in your book. So the main task of this are to define the stakeholder's needs and requirements, okay? The stakeholder is the customer, the user, whatever, right? And they can be different people, and so you need to realize that. There can be people who are the customer who are not the user. Like for instance, in the NASA world, SLS, the customer really is NASA. Boeing has to be responsible to Marshall Space Flight Center. But the user is the astronaut, you know? So those can be different people, and the stakeholders can be both of those. And there can be other stakeholders as well. Like for instance, for us at NASA, stakeholder is the American people, Congress, you know, all those different people can be stakeholders. So you have to figure out, and sometimes it is difficult to figure out which one is your stakeholder, or who is your stakeholder, and who are the most important stakeholders to make sure you make happy. Right? But you first work with them to figure out the needs and the requirements, right? You then perform a feasibility analysis. You can perform a high-level requirements analysis. You do some system-level synthesis, and you do a review, right? And make sure everything's good to go. So if you look, a lot of this stuff is the stuff that you're going to do for your group projects. So we're going to take you only through this stage, really, in IPT next year, in senior design. So that's the part I'm going to have you focus on for your group projects. So that's why it's important to me. So there is the top-down process where you identify needs and objectives of the stakeholders, requirements and functions of the system. So you start with the needs and that of the stakeholders. Then you begin to lower down and go into, it's a top-down, right? So you then go down into functions and what those are of a system. And we'll talk about this more in chapter 3. So I don't want to go into a lot of detail, but there's functions of the system. And then we end up going into like requirements and stuff of the system. There's requirements and functions, and depends on which one you say comes first. It's like the chicken and the egg, really. I like functions. I really do like functions because there are actions that must be performed, but you don't have a known solution yet. And I really like functions because of that. The bottom-up process is basically you assess the functions and you synthesize them into groups. So you can start at the bottom and say, oh, these are different functions. They must come together into a group to do a overall function. I like the bottom tops down approach. I think you get in trouble if you do bottoms up because you forget things. If you start top down, there's no way to forget something. You've got everything out there. You can look at all of it. The result is basically a functional baseline or a list of all high-level requirements and high-level functions of the system is what you want to get out of this phase, this stage, right? So you want to make sure you've got all that listed in some form or fashion. The stakeholders in need of unification. System engineering almost always deals with poorly defined problems. When the customer, the stakeholder, the user, whatever you want to call them, comes in, they really don't give you a really clear set of instructions, And so you've got to sit down and figure it out for yourself. Like next year, we're going to tell you to go to Europa and conduct some science. That's it. So from there, you have to figure out what all to do. And so that's why the system engineer's job is to sit down and go, okay, what do we really need from the stakeholder? What do we understand? What do we need to do? So the first step is to identify the stakeholders, translate fuzzy ideas into clear definitions of the needs, problems, and objectives. You might sit down with the stakeholder at a table. I have done this before, and they thought they wanted something. As you start talking to them, it begins to morph into something else, right? So those fuzzy ideas can then start changing into something more solid, and they have a clear picture. You just got to get that picture out of them and know what it is. System engineering addresses the needs not only of the client or customer, but also of others who are affected by or able to impact the system, right? So you got to worry about everybody when you're doing this. So system engineering has to do that. So the customer, the needs are there of them, right? But the system you create could affect other people in the world. So you got to be able to figure out what that is and how to minimize that as much as possible, because you got to make sure they're all okay with it too. So all that has to do. Like I said before, identifying the customer might not be easy, because then you've got to sit down and figure out exactly. You can generally know the group of people, but you need to figure out who is the most important person in that group to satisfy. And so that's what you're after when you do this stage. So basic questions that you need to ask during this phase is, how did the problem or need arise? That can then lead you to figure out what actually the goal is, right? What the need truly is, by sitting down and going, well, why is this important? That will help you figure that out. Who believes it to be a problem or feels it feels the need to do it, right? Because that who is probably your stakeholder, right? Is this the root problem or need, or is it a manifestation of some other deeper problem? That could be true too. So you can sit down with them and figure that out. Then you might really figure out, oh, it's a different kind of need that you have. It's not the need you actually stated, it's something else. And that happens a lot. Why is a solution important, right? Is there some overarching why out there? Why is it important? How much money will it save? What is the value of the system? All of these are very important things to know, right? We just don't create crap for crap's sake anymore. We've got to have some why, right? If you know Dr. Tippett used to do this a lot. When someone would do a dissertation, he would actually sit down at the end of it, because you've done all this work, and go, so why do I care, right? And that's exactly the same thing with this. There has to be some reason why we're doing this, and so that'll help you figure it out. And then it'll point you directly into the need to then figure out what the customer really wants. So how important is the need? Would resources be better applied to another need? All of that has to be thought of, Now, in the DoD NASA world that we mostly live in here in Huntsville, this is usually already picked because Congress told us it was important. They gave it money. They gave it resources, right? So we have to trust their judgment that they did what was right, right? So that can really help us. But in other cases, some of you said you could go in the commercial world. That might be the thing you have to figure out is, do you really need this thing? Do you need it now too? That's another step. Or could we wait 5 years and do it? That's the kind of thing you have to sit down and think about when you're doing this. Inside this is requirements definition, right? Inside this stage. So you got to learn how to define requirements. So requirements specify what the system must do and become the targets that the system designers seek to hit, right? So it's the stuff that they must do. I'm an old school requirements person, so I believe that anything that says shall in a requirement specification, it must do. Anything that says must or will do is a nicety, okay? That's what I was taught growing up in requirements development, in requirements definition. And so that's what I want you to do too. You're going to create, in the RFP, you're going to create a spec, and I hope, want you to make sure and put the shalls as things that must be done in this thing. So that's what I want you to do. I'm the old school guy. There's a lot of debate right now, especially in NASA, about getting rid of shalls. I'm not in that favor of that. I think the old way was a good way. I'm going to hold fast to my belief. So the shalls are what's important. The high-level requirements incorporate everything important about the system. So you start with a very high level, start with the need, and then work down, right? Just keep decomposing is what it's called. And you will continue to make more requirements and more requirements and more requirements. We have parents, we have grandparents, we have children, likewise, right? And so you can have all that. You can have them all linked together. And so that's what this does. There are objectives within these requirements that elaborate on the need and define the overarching aim of the system, right? They're usually necessary to define. It's usually necessary to define several objectives to fully specify the system. Usually the system has several objectives in mind, and so you got to have them all to really understand what this system is supposed to do. They are elaborated in terms of a set of requirements. So you can take the objective, right, and then create requirements from the objective. So everything flows from the objectives and the needs. Everything does. If you have a requirement that is not linked to an objective or a need, it should not be there. Okay? Everything should support what the system is supposed to do. If you have a requirement that doesn't support the overall objective and the overall need, then it's not necessary. You've added something too much, and you'll eliminate it. Okay? There's also the life cycle that will generate requirements, right? And so issues of how the system will be built or produced, tested, distributed, marketed, financed, operated, maintained, and ultimately disposed of are a part of the requirements, okay? And so you need to remember that. So all of these are going to give you requirements. How is it going to be built? How is it going to be tested? All of that is going to start imposing requirements on your system, so you can look at those. There's also operational modes will give you requirements. So operational modes are that systems basically operate in different environments and in different ways. And so those are operational modes or scenarios of operation, or also we call them at NASA operational concepts, okay? So you could have ConOps, or operational concepts is also another way to look at this. So those will impose requirements on you as well. All of that comes to pass. There are constraints. Constraints impose requirements, right? So every system is constrained. There's policies and procedures and standards, right? If you work for the federal government, this is your life. You have to worry about all of those. There's treaties, there's all kinds of things we have to worry about. So all that's out there. There's available materials, knowledge, and technology. Big ones, right? So materials, if you wanted to create something out of, unobtainium, it doesn't exist, so you got to change it. So that's the deal. Knowledge and technology. We can only do certain things with technology, and there's only things available to us, If you need a system to be in operation in the next 2 years, probably the technology's already been invented to do it, If you need a system that's going to operate in 25 years, then you might have some lead time to create a new technology to do it for you. But the requirements will tell you that you need to do it, right? And then there's also limited time, funding, and resources. Those are always put in as requirements, right? The mission shall cost no more than X billion dollars. It must be done by this date, And then there's resources. You can have no more than this many people, and you can do all this, right? All that comes to pass. And so the last one is interfaces, right? Because remember, that system has subsystems, right? So those subsystems have to talk to one another. That's an interface. And so right there is requirements, right? So it occurs whenever a system receives input from or provides output to another system, right? Or subsystem or element. All of those are requirements as well, right? Like for instance, if you have a spacecraft or something that would have went in the space shuttle. So that's a system, right? There's something that went inside the cargo bay of the shuttle. That's a system. Well, it has to interface with the shuttle. So there's requirements. There's interface requirements there. So all that has to happen as well. So there's all this that happens to develop requirements. So really, people always, this is pretty hard to do, people say, to figure out requirements. But just go through this list and you can start to figure out requirements. You can figure out that there's that, there's this, there's this, there's that. And you can start answering the questions then, and you can develop requirements from it. Okay? So requirements should address the needs of all the stakeholders, right? They say in this book to create what's called the stakeholder requirements document. I've never seen the stakeholder requirements document in my life, and they call it SRD. That's confusing to me because an SRD in NASA's vernacular is the system requirements document, which is the next step. So I just call this the list of customer needs, okay? So I'd create that list, and then from there you can start creating requirements from all those needs. So basically this list has all the stakeholder requirements and has to be readily understandable. It must be understood by both you and the stakeholder, okay? And this is where English is fun because the stakeholder can say something, you write it down, and it still means something totally different to you. So the best way I've always learned to do this is when I sit down with a stakeholder, I regurgitate back what I think that meant, okay, in my own terms. So therefore, we clearly have it all defined up front, right? So that's that document. I just call it a list, but they have it as a document. I don't particularly do that. I've never seen that happen in the real world. So next step is that feasibility analysis, right? We got those requirements, so now there's feasibility. So what are the available alternatives to satisfy the defined needs, objectives, constraints, and requirements? And all the alternatives feasible, right? So this is where you create a big tray tree, and then you hack the limbs of the tree. And this is what you'll do in the feasibility analysis study for me, is you're going to do this. You're going to figure out what are all the alternatives, right? Define the needs that can take all these things, and are they feasible? And feasible is in the eye of the beholder. So we'll define what feasibility means. Then the next step, you identify the alternative high-level solutions for the needs and requirements, and then you evaluate them in terms of cost, risk, effectiveness, and benefits. And that's exactly what you'll do for me. You'll end up looking at cost. You might look at risk a little bit. You're going to look at effectiveness. So for me, that's called performance. So how much payload can we get on the surface of Europa, stuff like that. And benefits. So what's the benefit of doing that too? And sometimes you got to weigh all that, right? So you'll create figures of merit. You'll do decision analysis. All that's going to be a part of feasibility analysis for me. And I want you to really focus on that over the semester because that's the big project for me that you're going to do. And once you do it, you'll be definitely ready for next year for IPT. In requirements analysis, basically that's the process of defining the functions that the system must perform and that the physical characteristics it must possess to meet the customer's needs, right? So you begin with the system and you start figuring out what functions it must do, what actions must it do in order to make it work, right? And you also need to know what the physical characteristics are to make it happen. It can only be this big, it can only weigh this much, it can only do that, right? That's the physical stuff. Then what must it do, right? You don't need what it could do, you want what it must do in order to achieve the need, right? So the document they call the system specification is what this does. All these functions and all these characteristics, I call that the system spec or the SRD, the system requirements document. There's three kinds of requirements that are usually listed in this thing. There are functional requirements, which is what we talked about, performance requirements, which are kind of the physical characteristics, and then there's verification requirements, which are how do you make sure the system does what you told it to do? Are you sure the design does what you mean it to do? That's the verification requirement. So functional requirements specify the functions that the new system must perform to meet all the requirements from the customer, right? It includes support, operate, and maintain the system. The best tool I know to use is called a functional flow block diagram. It's literally in the book, it shows you, and I would draw it, but I don't have a board. There are blocks, and you put the functions. This function leads to this function, this leads to the next function, and then you can decompose those functions even lower. There's tools to use for this as well in industry, doors, cradle. There's all kinds of things out there that you can use to do this for you, but you can literally draw boxes in PowerPoint if you had to and put these functions in it and make it work. So that's the FFBD is what we call it. So each block represents a function that the system must perform to satisfy the objectives of the requirements, right? And this is a function. This is not the solution, okay? These are actions that the system needs to take. These are not solution-based. And you gotta remember that, because most people, when they start this process, they have a solution in mind. You don't want that, because then the solution you have in mind, once you create the functions and you create the requirements from the functions, you get the solution that you had in your mind. And maybe it's not the best one. So you got to remember that when you do this. It's a very hard step to follow. Okay? Performance and verification requirements accompany functional requirements. Functional states what the system must do. Performance states how well it must do it. Right? So that's the difference. It says do it. Functional. Performance says this is how good you better do it. Right? So it adds some more data, some more detail to it. Is really what a performance performance requirement does. Performance usually is specified in physical parameters. So now you know numbers, right? So you can say in a function run, but now in a performance requirement, you're going to say run 22 miles an hour. Whatever, move 22 miles an hour. So that's the difference in the two. Each performance requirement has a verification requirement, which is basically a procedure, which procedures, measures, and tests to verify that the performance has been met. That's the verification part of this, right? So you create some sort of analysis, some test, something that then verifies that you have the performance that you wanted from that requirement, right? Throughout the conception stage, reviews are conducted to verify and approve the system level requirements. So all this goes along, and you come to the system spec review, if you want to call it. They call it I forgot what they call it now in NASA terminology. But there's a system, a requirements review, or SRR, system requirements review. That's what it's called, SRR. And so we stop and we go, are these the requirements, at least the high level ones that we need? And we baseline those, and that's what the SRR does. It also gives us a pretty good picture of what the system looks like. And at the same time, we've done this feasibility analysis to at least know, yeah, it looks like we could do this. That's what kind of feasibility does. It's it's doable. We can still do this. It's feasible. We can do this kind of thing. And so that's what we do. In stage 2 is called preliminary design. So you can see how much I focus on stage 1. Stage 2 is preliminary design. So you pass that review, you pass that hurdle, and we go on into preliminary design. The system level requirements are translated into design requirements for the subsystem. So now we take the system and start breaking it down into pieces, right? And the subsystems have requirements, the elements have requirements, and that just continues to go down through the details, and you go into detailed design like that, right? Trade-off studies are performed of the high-level elements comprising the system, because then you can figure out and make sure you've got everything correct. That's the right element or system to use. This is the right thing to use. We can get it all together. The system level requirements are allocated among the subsystems, and when that happens, you create the interfaces, right? So now you've got these subsystems, because the system is so big, it just can't do it all. So each subsystem comes into play now, and they have to participate, right? They got to play together, and they create interfaces. And that, by far, is the place where the trouble happens. Interfaces are always where there's an issue in any design. A subsystem by itself works perfectly, but if it can not talk to the other subsystems and know what to do with them, then that's where the failure always happens in a system. So that's what to keep in mind. So interfaces are very important to watch. Okay. Stage 3 is detailed design and system development. So there's further description of the subsystems, assemblies, components, and parts of the main system, and the support items, right? We're just continuing to make more detail. You move from concepts on paper to a design that is ready for fabrication and production, right? So it includes checking the operation of the subsystems when combined into a complete system. You evaluate the validity of the design assumptions, and you pay close attention to those interfaces, right? So all that happens because now it's real, it's hardware, it's becoming a design. So everything's coming together. Stage 4 is system construction and or production. So in production, you can have different things. You can mass produce it, in the commercial world especially. You might produce in limited quantities with different features, or you might just build one of them. At NASA, that's what we do. We build one of everything, We don't build a lot of things out there anymore. And so that's our kind of way. Mass production in this area is DoD and like Toyota and places like that. They do it, but we don't really do it much in the aerospace world, and especially in the NASA world. Once a design is approved or frozen is when you can start production, okay, or construction. At NASA, that is defined as CDR, Critical Design Review. It's called 80% design complete. So the design is only still 80% complete, but there's so much definition, you can then begin to cut hardware, is what we call it. So we actually start to fabricate things at this level. It involves acquiring materials, managing inventory, and controlling production and construction operations to uphold the performance, quality, reliability, safety, and other requirements that you need, right? So when you're fabricating a plane like Boeing is, they've designed it and went through stage 3. Now it's in construction and production. So now all this stuff has to be worried about. Do they have enough composite material? Do they have enough aluminum? Do they have it in inventory? Have they got the right inventory coming in? They've got all these issues of parts coming in and out. Controlling production and construction operations, keeping the tolerances tight, everything's working well so that you uphold performance, so you got the right vehicle, weight, quality, reliability, safety, and other, right? All of that has to happen like when Boeing makes these planes. It's got to be quality, good quality work because people are going to fly on it, and that affects reliability and safety, right? All of that has to happen to make this work. And last but not least is stage 5, system operation and support. So the customer operates the system until it ultimately wears out or becomes obsolete, but the developer usually continues to provide support during this option. So that's how when it wears out, we got to keep helping them keep it going, right? This also includes, it's not in the book, it includes disposal, and that can become a bigger issue for you. What happens once we have used this thing, its useful life is done, right? We can't just throw it away, bury it in the pit somewhere anymore. We need to understand the ramifications of that because that can impact the design, also in the early stages. So we will talk more about that when we go into chapter 3, which we'll do when I come back from Paris, right? So this concludes chapter 2. Hopefully, I think I took about an hour. You were able to follow along with the notes in the posted on Angel. Hopefully this is kind of jiving now. You're understanding this a little bit more because this is starting to show you sort of the group projects and where we're going to go from there. Hope you guys have fun while I'm gone. I'll be in Paris, and then I'll be around Huntsville and everywhere else, and I will see you back on, I believe it's the 30th. Yeah, that's the day. And so, au revoir. See you guys later. Bye.